Okay, it's time for our fourth and final example using this same circuit. I have one more example in today's lesson, but it will involve a different function. But we're going to look at this same circuit for the fourth time. Now our purpose is to try to minimize or simplify or reduce this logic circuit. Now, you can ask yourself the question of what are the criteria for reduction? I'm going to use the criteria which is that I want to minimize the total number of logic gates in this circuit. And so you can see here I'm starting off with 5 logic gates. Sometimes the inverter is considered to be not as much of a gate as the others, but for our purposes, we're going to say there are 5 gates. I want to try to reduce that down to 4 or even 3 if possible. In the example in the lesson notes, we went from 12 gates down to 1. Well, full disclosure, that was kind of an example that was written to be really easy to simplify. This is actually more of a real-world circuit. This is the sort of circuit where we might be able to find there'd be some improvement. We're definitely not going to get it down to just 1 gate. Let's see how we can do. So we've already studied this circuit before, and so we've already seen that the function, the sort of raw function, is A NAND B or C NOR D, and then that's then ANDed with C or D. And then in the previous example, for the truth table, to get it into the SOP form, we already did a brief simplification of this. I'm going to go ahead and replicate that simplification just so that we can see the entire example here from scratch. So I can see that if I'm going to use De Morgan's theorem, I can break this first A NAND B. So this A NAND B can be broken up into not A or B, or not A or not B. Remember that if you want to break up the large bar that appears across that entire term, you can do so. You can break it into 2 smaller bars, but De Morgan's theorem says you must then replace the AND gate with an OR gate, and that's what we've done here. So I'm going to have OR. Now I'm going to break up this term. So that term C NOR D, I can break that up into not C, but now instead of an OR gate, it has to be an AND gate. So it's not C and not D. Well, that entire expression is in parentheses, and then it's ANDed together with C or D. Now you can see here that there are 3 terms in this first expression, and there are 2 terms in this second expression. So if I'm going to expand this out, I'm going to use distribution here. I'm going to be able to get 3 times 2 is 6 terms. So I'm going to go ahead and write those 6 terms out. I'm going to cross multiply not A with C, so I get not A and C, or not A with D, or not B with C, or not B with D, or not C and not D and C, or not C and not D and D. So I started with an expression of 3 terms, multiplied an expression of 2 terms. I ended up with an expression of 6 terms. And as we talked about in the previous example, this term right here includes both a not C and a C. And it doesn't matter what else is in that expression. There is absolutely no possibility that anything will ever be both C and not C. So that goes away. Similarly, here we have a not D and a D. That's simply not possible. And so that one's also going to go away. So I'm left with F is equal to not A and C, or not A and D, or not B and C, or not B and D. Now, if I criterion were to get this into the simplest possible sum of products form, we're done. But the criterion that was set out at the beginning of the problem was to try to design it so that it would have the simplest or fewest number of gates. And so I'm going to try to go one step further here. You can see that the first 2 terms both have a not A, and this third and fourth terms both have a not B. So let's go one step further and factor the not A out. So not A and C or D, or not B and C or D. Now we just happen to get very fortunate there that the C or D appears in both of those terms, because now we can simplify it even further. F equals not A or not B and C or D. And that's almost as simple as we can get it. We would need one inverter, two inverters, an OR gate is 3, an OR gate is 4, an AND gate is 5. We actually wouldn't save ourselves any total number of gates, but we can still have one more trick up our sleeves, and that is that we're going to apply reverse De Morgan's theorem. And that is that rather than having the two bars over not A and not B be separate, we can mesh them together. But again, we have to change the nature of the function between them. So here I'm going to say this is A NAND B. All I did there was to go in the opposite direction of what we have done in the past. In the past, we've broken the bar in half. Here, I've combined the bar together. So it's A NAND B and C or D. Now, if you've been paying close attention, you probably think to yourself, it seems like we expanded and expanded and expanded, and then we contracted and contracted and contracted. And that's true, but the key was in this step right here, we were able to identify two terms that could go away. And so I can actually now represent this function. I can have A NAND B. So here's A NAND B. I can have C or D. So here is C or D, and then I can AND those together, and that will give me F. So you can see that my final answer here involves only 3 gates. So this circuit right here is identical in function to the larger circuit that we had at the beginning of the problem, which required 5 gates. So by some diligent application of Boolean algebra and De Morgan's theorem, we're able to reduce down from 5 gates to 3 gates. That's almost a 50% reduction. And if we're making millions and millions of these circuits, I'm sure that the boss will be very, very happy to have had that reduction.